Okay, this section is about the finding convergence or divergence of a series, infinite series. Um, in this case, we're going to use what's called a p-series, and the p-series is founded on integral testing. But basically, let's review some integration of some infinite series. Quick little reminder: what we're doing is we're going to graph the 1 over x curve, which looks like this, and we're trying to find the area under the curve from 1 to infinity, but this is never bounded, so to find its area is the question mark. Can we do that? And the way we did that is we took the limit of this, but remember, we can't have an infinity here. We're going to call this a and say the limit is a approaches infinity. This one is pretty straightforward. It's integration, limit as a approaches infinity of L in absolute value of x from 1 to a, which equals the limit is a approaches infinity of L in absolute value of a minus L in absolute value of 1. Absolute value of 1, L in 1 is 0. And this is ln infinity, which is infinity, which basically implies that this function's integral, the area under its curve, is unbounded, so it's divergent. Now we'll look at this one. This one is the same thing, only notice now the power is a power of 2. Okay, its area is still this curve, but it's still got that issue where going from 1 to infinity, it doesn't have a bound. The question is it bounded enough to create an area, or is it divergent? So this is what we did last chapter, is basically leading into this section here. So if I take the integral of this, remember this is x to the negative 2. I'm going to call this a, make that this limit is a approaches infinity. For formality purposes, that's what we do. Now I'm going to anti that, so add 1, divide by the power from 1 to a, which equals the same thing as negative 1 over x from 1 to a, which is negative 1 over a minus negative 1 over 1. Remember, now we have the infinity, which gives me 1. This time, when the power is 2, notice that in fact it converged to a value. Hence, the series of the 1 over x squared will also converge. We don't know particularly what to. This does not imply what it converges to. This is the area under the curve. But however, it does tell me that in fact it does converge. One more integral just to kind of feel out this stuff. Now what if I change the power now down here? The fractional power to 2/3 down there. So it's a number less than 1. Let's see what happens when I do this integral. Once again, let this be a, and you're doing the limit as a approaches infinity. I'm going to write this as x to the negative 2/3, and now when I do the anti, I add 1, divide by the power from 1 to a, which equals 3 x to the 1/3, 1 to a, which is equal to 3a to the 1/3 minus 3. Now remember, this is the limit, so this is infinity. Any infinity to the 1/3 is infinity. Subtract 3, which is infinity, which tells me the area under this curve is unbounded, it's divergent. That leads us to add. Now we're going to do series. For a series, we have the p-series test. This is also on your flashcard, so don't panic. It's all in print, easy to find. The p-series says if I'm taking a series that's 1 over n to the p. Notice that the n is not in the exponent, so it's not going to be a geometric or a ratio. Geometric and ratios, the n is in the exponent. It's geometric or ratio. P, the n is down here. P is a number, and if it's a number that's greater than 1, no matter what, it's convergent. Now, you're not going to always have a 1 on the top. You're not always going to have this on the bottom. We can do comparisons as well, but the key thing is that if you have something with a power of greater than 1, it will converge. If it's this number here is less than 1 or equal to 1, it's divergent. So, very similar to the two integrals we did, I can ask you to answer the question, does this converge or diverge? Again, if we find it convergent, only if it's geometric can we find what it converges to. This one is not geometric. So what you have to do is identify the series. Now, I typically what we do is I typically do an nth test. The nth test, and I'm sure you've seen me do it before, nth test is just take the limit as this approaches infinity. If it equals 0, I don't know anything. But I do know this, if it does not equal 0, I automatically can conclude that this diverges. So by the nth test, I take 2 over infinity, which is equal 0. So the nth test is not conclusive. That doesn't tell me anything. It only tells me something if it does not equal 0. It'll tell me it diverges then. So right now I don't know anything. So what I'm going to do is I'm going to look at this. I'm going to say, oh, wait a minute. This is the p-series. My p is equal to 1. Therefore, by p-series test, this will diverge. Now, technically, the integral that I did is the integral test, which in fact verifies it, but this is all I have to do. On your AP test, they give me this series. I'm saying it diverges. Why? By the p-series test, p is equal to 1. They give me a simple one like this, and they do that too. They give me a simple one like this. I say, the n's down here, it's not geometric. It's not in the exponent, so therefore this is a power series. My p is equal to 2. Therefore, by p-series test, it converges. That's all I have to do. Now, are they that simple? No. But if you look at it carefully, anytime I add or subtract of constant, it's kind of irrelevant when we're going off to infinity. So that's kind of where we consider comparisons. Now, I'm not going to go through the whole comparison thing and elaborate because I want to get to the punchline here. I want you to be able to produce this. So the question here is, okay, here's a series. And I say to myself, does it converge or diverge? I notice that the n is not in the exponent, so I cannot consider geometric or ratio test. So what I'm going to do is, if I didn't start right away recognizing this looks like a p-series, except for it has a stupid +7, I would first start with an nth test. The nth test, again, is take the limit as this approaches infinity. The a sub n term approaches infinity. And if it does not equal 0, I can conclude automatically it diverges. If I take the limits of this, I do get pi over infinity, which is 0. That makes this inconclusive. The nth test doesn't help at all. I wish it had not been 0, then I could have said right away it diverges. So this function, the a sub n function, compares to a comparison function Cn. It's like this function. The plus 7 is irrelevant. Whether it's above or below is quite irrelevant here. I'm not going to get into the details. It can be considered a direct comparison or a limited comparison, but it is a comparison. These two are very much alike. So once I identify the comparison, these are much like each other. This one, this Cn, the comparable function, diverges by p-series test. Because the p is equal to 1. Therefore, a sub n diverges by comparison test. Notice this doesn't require a whole lot of work. It's just simply identifying it. So I recognize that this is not in the exponent. I can compare it to this function, which is a p-series. I know that's not a 1, but remember we can move the 1 out. Well, what happens if I have an n minus 7? Does it change? No. It does change whether it's above or below the comparable function, but this function still is going to compare. So this would be my a sub n, my comparable function, my Cn, would be pi over n, and basically I would have exactly the same explanation. I would say that Cn diverges by p-series test. P equals 1. Therefore, an diverges by comparison test. Whether it's direct or limited is irrelevant, okay, at this point. Okay, now what if we get into some more complicated ones? What if I get something like this? First of all, I notice that the n still is not in the exponent. I don't want a geometric. It's not going to be geometric, and I certainly won't be able to use a ratio test. However, I note by comparison, I notice this is irrelevant to the problem. We're going off to infinity, and then subtract 1 is irrelevant. I can't do the nth test. The nth test kind of reveals a comparable function. So if I do the nth test, I'm going to take the limit as the a sub n, as n approaches infinity of the a sub n. So I'm going to take this and I'm going to take its limit. If I do that, I get infinity over infinity. L'Hopital's rule applies. So I'm going to take the derivative of the top. And that's the one I just said you just need to know. And then the derivative of the bottom, which produces the a sub n function that's comparable to it, would be 1 over 10 x to the 4 times the square root of x, which is in fact 1 over 10 x to the 9 halves. Now, if I take the limit again, limit as n approaches infinity, which is the nth test, I get 0. That's inconclusive. And I appreciate that's inconclusive. However, it helps me recognize a very comparable function to this. If I take a look at this and I consider that the -1 is irrelevant, then this function compares to this function. So this is my a sub n, and I'm going to create a comparable function, which is this one. And by simplifying that, I'm going to get 1 over, that's into the 1/2. That's into the 1/2. So 1/2 subtract 5/2 is -4/2. So n to the 9/2. No coincidence. See that nth test, how it revealed this? It kind of the nth test reveals a very comparable function. So now that I have this function, I can see that the p here is 9/2. So Cn will converge by p series. Note that the p is 9/2. Therefore, my original function a sub n converges by comparison. Hopefully everyone was good with that one. And I think that's all I needed to demonstrate. There are multiple different examples that we can try. And you don't have to do any bookwork off this one. Wait until I demonstrate the next set, which would be the harmonic. Or I'm sorry, not the harmonic, the alternating series test.